In the previous chapter, we covered the technical specifications that define the performance of an LNB dot. In addition to them, there are multiple factors beyond these technical specifications that must be considered on which LNB is the best option for a specific setup. Performance, price, connectors are a few, but where do we start? To help in the process on making that selection, we broke down into key considerations what we believe will guide you through this process, such as input band and frequency range, stability and reference, noise figure installation, and additional considerations. How to select an LNB. Chapter 3. First of all, we have to consider the input band and frequency range. This is very important, otherwise the signals we expect to receive will not be properly handled by the satellite receiver or modem. As we mentioned on the previous chapter, it was described that the satellite bands are divided by frequency range in C-band 4 to 8 GHz, X-band 8 to 12 GHz, Ku-band 12 to 18 GHz, and Ka-band 26 to 40 GHz. Because the function of the LNB is to downconvert from this band to a standard L band that the satellite equipment can work, it is important to understand which band the system in question operates. The wavelength related to the frequency has a relation to the mechanical installation of the LNB. The waveguide dimension is associated to that operational frequency, and sometimes it is easy to identify which band the LNB operates by observing the dimension of the LNB waveguide. The higher the frequency, the lower the wavelength and its associated dimension. For example, the C-band LNB operating between 4 and 8 GHz will have a larger waveguide size than a Ku-band LNB. Additionally, within these defined bands, there are different subbands with a smaller frequency range, depending on local regulations on spectrum assignation for satellite communications. In other words, LNBs within the same band can have a different frequency range depending on the region they are. For example, a Ku-band LNB typically used in Asia operates in a different frequency range than the ones used in Europe. On an LNB, the amount of frequency conversion is determined by the local oscillator, or abbreviated as LO. You will find this parameter in the LNB technical specification. Internally, the LNB will mix with the input frequency to be translated to the end frequency within the L band range. Fortunately, this process can be easily calculated by adding or subtracting the LO value. For example, if the input frequency is 9,000 MHz and the LNB LO is 8,000 MHz, the output frequency of the LNB will be subtracting 9,000, 8,000, which is 1,000 MHz. The second parameter is the stability and reference. These parameters are also related to the signal bandwidth used. The bandwidth is the amount of information is contained in a signal expressed on hertz. On large signals, the precision of the downconversion might not require to be high. However, the smaller the bandwidth, it will require to have a higher precision to avoid interfering with adjacent signals, and for the equipment to properly receive information on the signal. The conversion stability is related on how much deviation and oscillation the converted signal has to this desired frequency. To achieve this precision, the LNB requires a reference to make the downconversion from the satellite band to a generic L band that the satellite equipment uses. The reference is typically a 10 MHz reference signal. There are LNBs that include an internal reference. Depending on the material and the components used, the conversion can have a higher precision than others. For example, LNB using a dielectric resonator oscillator, or VRO, are very simple design and makes them affordable. Crystal-based reference like OCXOs and VCXOs are more sophisticated and provide higher stability. The most precise and stable conversions can be achieved by using an external reference LNB. The reason why is because the reference could come from an equipment with higher precision signal. You will find that the LO stability is not in the technical specification for external reference because it is dependent on the reference that is injected. On the previous chapter, we mentioned that the LO stability sometimes can be found in some specification sheets as ppm, which is the variation ratio over the LO conversion frequency. Keep in mind, it is a different expression of the same content. The next important parameter is the noise figure, sometimes also called as noise temperature. Although these two parameters are not the same, they are related, and there is a formula to calculate the equivalency between them. The performance of the system including the antenna and its components, are the sum of all the gains and losses that the signal passes through. Noise temperature is considered a loss since it is the amount of noise expressed in terms of temperature that it is introduced to the system. The LNB noise temperature is the main noise contributor to the system. The lower the noise temperature, the lower the amount of noise is added to the system. Total gain of the system, or G over T, also expressed in terms of temperature, considers the gain of the antenna, including the gain due to size, frequency used, and its efficiency, minus the loss of its components, like the LNB noise temperature. That is the importance of the noise temperature and determines the maximum amount of noise that the LNB can introduce to the system without affecting the performance overall. Another important thing to consider on an LNB is where it is going to be installed and how it is going to be powered out. As we have mentioned, the operational frequency determines the waveguide size, but other things to consider are typically the connector and the cabling that the system has. Which equipment will be providing the LNB voltage to power it up, and if this voltage is within the LNB operational range, and if this equipment can provide an adequate 10 MHz signal, even external reference LNB is used. The rest of the specifications may or may not affect significantly the system performance. Some applications might require considering them to ensure proper performance. One of them is phase noise, which is the noise introduced at various frequency distances on the converted signals by the oscillator. This can significantly impact the bit error rate, or BER, especially at more complex modulation schemes. The SWR is the efficiency of how a wave is properly inserted to a component of the transmission line. An inadequate coupling might cause reflections between components that can distort the original signal. The form factor is something to keep in mind, especially working with small and compact terminals, weight dimensions, and the form factor could potentially be a limitation, and shall have a special requirement if needed. The input voltage and the current consumed by the LNB are sometimes important to consider where the equipment that supplies the voltage has limitations on the current that can provide. Now, let's talk about applications that might have additional requirements that are also important. Applications like maritime, where the LNB is installed on a ship that would require compliance for shock or vibration, or EMI/EMC. Airborne applications might require compliance to some altitude testing. Some of these special requirements might need additional testing to meet a special certification to prove that the LNB can meet them. Some other applications might also require to comply with a wide temperature range, either installed on a very hot, cold, or extreme weather. A quick reminder, the LNB performance changes with temperature. For mobile applications, where a satellite terminal requires to be transported around the world, they might use multiple LNBs depending on the region they are going to be used. An alternative is to use LNBs with multi-band capabilities. These LNBs have the ability to switch between multiple LOs within the same unit through the input voltage, normally 13, 18, or 24 volts, in combination with a tone, usually a 22 kHz tone. The combinations between the tone and the voltages allows the LNB to switch between the internal bands. Make sure that the RF equipment and the setup has this capability if you are planning to use these types of LNBs or externally control them with a universal LNB controller, or ULC, that can be added in the chain as a separate component. One last consideration that would affect the performance of the LNB is external interference. Depending on other RF sources, antennas, electrical installations, or terrestrial communications, you might require considering an additional filtering to improve the performance of the LNB. Some LNB options provide additional filtering within the subband. One of the most discussed topics that affect satellite communications nowadays, especially the C-band, is the 5G communication. Alternative LNBs with additional filtering to reduce and mitigate the 5G interference on a satellite antenna are now on the market. That will be covered in the next video.